The same planning document that still talks about coal, steel, and semiconductor self-sufficiency now quietly embeds something that sounds almost out of place: biological manufacturing as an industrial pillar. In other words, a system that once measured strength in megawatts and tonnage is now assigning strategic weight to engineered microbes. It looks contradictory until you realize what's actually being rewritten. China has been updating its industrial roadmap through the 14th Five-Year Plan framework, coordinated by bodies like the National Development and Reform Commission. On paper, it still reads like classic state-directed industrial policy: energy security, advanced manufacturing, supply chain resilience, the familiar architecture of a rising industrial power. But inside that structure, biomanufacturing is no longer framed as emerging science. It is being positioned as infrastructure. That distinction matters more than it sounds, because infrastructure, in planning terms, does not mean innovation. It means substitution at scale. What China is effectively doing is treating biological processes, microbial fermentation, enzyme-driven synthesis, engineered protein production, as potential replacements for petrochemical supply chains, not supplements, substitutes. If that sounds abstract, it isn't. Industrial enzymes already replace chemical catalysts in detergents and textiles. Fermentation already produces amino acids and vitamins at industrial scale. The difference now is scope. The five-year plan language points toward entire categories of materials being shifted into biologically mediated production pathways: plastics precursors, specialty chemicals, even food-grade proteins that reduce dependence on land-intensive agriculture. And this is where the contradiction sharpens. A country still heavily exposed to imported oil, natural gas, and agricultural inputs is simultaneously investing in systems that could bypass parts of those dependencies entirely, not through extraction, but through controlled biological production. It raises a simple but uncomfortable question: is this diversification or structural detachment from global supply chains that were assumed to be stable? There is a human layer here that often gets missed in macro analysis. In Shanghai and Shenzhen-linked industrial zones, pilot fermentation facilities are being scaled with the same language once reserved for semiconductor fabs. Not because biology is replacing chips, but because both are now treated as controllable production systems, designed, optimized, and replicated. One engineer involved in pilot bioreactor scale-ups described the logic bluntly in a technical briefing: if petroleum supply is geopolitical, biology is procedural. You don't mine it, you grow it. That framing is doing more work than it seems. My view is simple, but not fully settled. This is not China betting on biotechnology as a sector. It is China testing whether biology can become an industrial substrate, something beneath manufacturing, not a branch of it. But there's a gap in that assumption. Can biological systems be scaled with the same predictability as industrial chemical plants without introducing new constraints in temperature control, contamination risk, and energy input that erase the theoretical efficiency gains? I'm not fully convinced the transition is smooth. The engineering optimism is real, but so are the failure modes that don't appear in planning documents. And the direction still points forward. The prediction here is not that biological manufacturing replaces heavy industry in this five-year cycle. It won't. The timeline is too short, the infrastructure too uneven. But the direction of investment suggests something more subtle: a parallel supply chain architecture that starts as redundancy and slowly becomes independence. The question is, what happens when redundancy stops being backup and starts becoming preference? Because once that shift locks in, it doesn't just change how things are made, it changes what a manufacturing power actually is. There's a tendency, especially outside industrial policy circles, to treat biomanufacturing as a futuristic label attached to labs and venture-backed startups. That framing misses what matters here. In China's planning language, the term is not descriptive, it is infrastructural. And infrastructure, once defined at the five-year plan level, tends to acquire funding gravity that most private sector interpretations never see. To understand why this shift is happening now, You have to look at what has already been stress tested. Between 2018 and 2023, China's exposure to chemical input volatility increased in ways that are rarely discussed in headline trade coverage. Specialty chemical imports from Germany, Japan, and the United States became less predictable due to export controls and compliance tightening in high-end materials. At the same time, energy price instability after 2022 made petrochemical dependence more expensive at the margin, even when supply remained available. None of this triggered a crisis. That's important. It created friction, not collapse. And friction is what industrial planners actually optimize against. Inside the Chinese Academy of Sciences ecosystem, biomanufacturing research has been converging on a practical constraint. If you can design a biological pathway that replaces a chemical synthesis step, you reduce exposure to upstream geopolitical volatility. Not eliminate it, reroute it. That distinction explains why fermentation and enzyme engineering are being treated differently than they were a decade ago. There is a specific case that illustrates this shift clearly. Amino acid production, particularly lysine and glutamic acid, has already undergone large-scale transition in China over the past 15 years, from chemical synthesis to microbial fermentation. Companies like Fufeng Group built global dominance in this space, not because fermentation is exotic, but because it is stable, repeatable, and less dependent on imported petrochemical intermediates. That success story is now being treated less as an exception and more as a template. And this is where the planning logic becomes more explicit. If one class of chemicals can be moved into biological production without loss of scale efficiency, then the question shifts from, can this work, to what else can be converted? Industrial planning documents tied to the 14th Five-Year Framework do not always name targets directly. Instead, they describe capability clusters, synthetic biology platforms, industrial strain engineering, bio-based material synthesis. The language is deliberately abstract, but abstraction in policy documents often signals optionality, not vagueness. Optionality at state scale becomes strategy. Now, there is a counter-argument that deserves to be taken seriously. Biological manufacturing is not a clean replacement layer. It introduces contamination risk, slower iteration cycles, and energy overheads that chemical processes do not always have. Scaling a bioreactor from lab to industrial volume is not a linear problem. It is a systems engineering constraint problem where small inefficiencies multiply quickly. Western biotech firms have experienced this repeatedly. The gap between works in controlled conditions and works at 10,000-liter scale continuously has killed more commercialization timelines than funding shortages ever did. China's planners are not unaware of this. In fact, some of the policy language reads like it was written by people who have personally seen pilot plants fail, which makes the current push more interesting, not less. My interpretation is that this is not a bet on near-term dominance. It is a portfolio hedge against industrial concentration risk, especially in sectors where chemical supply chains are increasingly entangled with geopolitical choke points. But I'm not fully convinced that biological systems scale into a true substitute layer for petrochemicals without hitting physical constraints that are being underweighted in policy modeling. Here's the open question I keep returning to. Are we looking at a genuine industrial transition or the creation of a parallel system that only looks independent until it is stress-tested under global demand shocks? Because those are not the same outcome. And the difference only becomes visible when scale stops being theoretical and starts being continuous. There's a point in almost every industrial transition where the story stops being about technology and starts being about constraints that refuse to behave politely. Biomanufacturing is reaching that point in China's policy architecture. On paper, the logic still looks clean. Microbial systems convert sugars into chemicals. Engineered yeast produces pharmaceuticals. Bacteria become living factories for industrial precursors. The appeal is obvious: modular production, lower reliance on imported catalysts, and theoretically shorter supply chains. But scale has a habit of stripping away elegance. A 2023 review published through Tsinghua University's Synthetic Biology Groups highlighted something that rarely makes it into policy summaries. Productivity in industrial bioreactors does not scale linearly with volume. Oxygen transfer limits, heat dissipation, and contamination probability all increase non-linearly as tanks get larger. In practical terms, doubling capacity is not doubling output. It is redesigning the system. That matters because China's five-year plan language is not talking about boutique production. It is talking about industrial substitution. And substitution only matters if it survives continuous load. There is another layer that complicates this further: feedstock dependence. Biological manufacturing still depends heavily on sugar sources: corn, cassava, glucose streams derived from agriculture or refined biomass. That creates a structural link back to land use and global commodity markets. In other words, the system that is supposed to reduce exposure to geopolitics quietly inherits a different version of it through agricultural inputs. This is where optimism and skepticism collide inside the same policy framework. On one side, there is clear progress. Industrial fermentation already dominates certain amino acids, vitamins, and enzyme markets globally. The cost curves in those sectors have been permanently altered. No serious analyst disputes that. On the other side, the jump from specialty chemicals to bulk industrial materials, plastics precursors, large volume solvents, structural polymers, is not just a scale-up problem. It is a thermodynamic and logistics problem. Energy still has to enter the system somewhere. Matter still has to come from somewhere. A quiet reversal appears here, and it changes the way the entire strategy is interpreted. What looked like a move toward independence may actually be a move toward different dependencies. Instead of oil and gas choke points, you get agricultural input chains, fermentation infrastructure, and highly specialized bioreactor ecosystems. The map changes. The vulnerabilities do not necessarily disappear. There is a human example of this tension that rarely gets discussed outside technical circles. In Zhejiang province, several pilot-scale biomanufacturing facilities have reportedly shifted from experimental output to semi-commercial production of bio-based chemical intermediates. Engineers involved describe a constant balancing act between yield optimization and contamination risk management. One line failure can contaminate an entire batch cycle that took days to stabilize. Unlike petrochemical plants, you cannot simply flush and restart without economic cost accumulating quickly. That operational reality sits underneath the policy optimism. My view is that China is not misunderstanding this constraint. The more likely interpretation is that it is accepting it as a trade-off, trading energy geopolitics for process complexity. Whether that trade is beneficial depends entirely on whether biological systems can be made resilient enough to operate like infrastructure instead of like sensitive laboratory ecosystems. I'm not fully convinced that threshold has been crossed yet. And this is the point where the narrative splits into two plausible directions. Either biomanufacturing becomes a durable secondary industrial backbone, not replacing petrochemicals, but absorbing enough categories to reduce external exposure at the margins. Or it remains a high-value niche layer that looks strategically important in planning documents, but never fully escapes the constraints of scale biology imposes. The difference between those outcomes won't be visible in announcements. It will show up in something quieter, whether output remains stable under stress, or whether every global shock still ripples through the system regardless of how many fermentation tanks you build. And that is still an open engineering question, not a political one. At this stage, it's easy to misread the entire biomanufacturing push as either breakthrough or overreach. Both readings miss something more uncomfortable. China's industrial planning system rarely optimizes for clean outcomes. It optimizes for redundancy under uncertainty. That distinction matters, because once you stop expecting a single winner technology, the 14th five-year plan language starts to look less like a bet on biology and more like a hedge against the fragility of petrochemical dependency in a world where supply chains are being actively rearmed. There's a reason the term synthetic biology platform keeps appearing in policy documents instead of specific products. Platforms are not endpoints. They are permission structures. They allow multiple industrial experiments to run in parallel without committing to a single outcome too early. Inside that framework, biomanufacturing is not competing with oil refining or semiconductor fabs directly. It is competing with uncertainty itself, and uncertainty is becoming expensive. Energy markets since 2022 have shown how quickly price shocks propagate into industrial inputs. Specialty chemical shortages during logistics disruptions didn't just affect factories, they delayed downstream manufacturing in pharmaceuticals, electronics, and food processing. Even when supply recovered, the planning assumption changed. Reliability is no longer guaranteed at marginal cost. That's the pressure point. Now, zoom out slightly. The China approach is not isolated experimentation. It sits alongside parallel pushes in semiconductor independence, energy security, and critical minerals processing. Biomanufacturing is simply the least visible layer of that same architecture. But visibility matters here because biological systems introduce a different kind of constraint profile than traditional industry. They are flexible but fragile, adaptable but sensitive to drift. They scale but not cleanly. Which brings us to the reversal that's easy to miss. What if the goal is not to replace petrochemicals at all? What if the goal is to ensure that no single input system, oil, gas, agriculture, even microbial fermentation, ever becomes a point of total dependency again? That interpretation reframes everything. It turns biomanufacturing from substitution into diversification of failure modes, not eliminating risk, but distributing it. My opinion is that this is the most consistent reading of the data. It matches the language of the planning documents, the pacing of investment, and the historical pattern of Chinese industrial policy. Never fully abandoning legacy systems, but always building parallel ones until redundancy becomes structural. I'm still uncertain about one thing, though. If biological manufacturing matures faster than expected in certain chemical categories, does it stay a hedge? Or does it start pulling entire supply chains into its logic because it is cheaper, cleaner, or more controllable at scale? Policy intent and industrial gravity do not always align. And that leads to the prediction I keep circling back to. Over the next 5-year plan cycle, biomanufacturing will not replace petrochemical infrastructure in any visible headline way, but it will quietly expand into the middle layer of industry, the amino acids, solvents, materials, and intermediates that sit between raw extraction and final manufacturing. That layer is where most of the global economy actually lives, even if it rarely gets attention. If that shift holds, the definition of industrial power changes subtly but permanently. Not who extracts the most resources, but who controls the most flexible conversion systems between raw matter and usable output. And once that definition changes, it doesn't revert easily. The last quiet irony is this. Biological manufacturing is often described as closer to nature. In industrial policy terms, it may actually be the most artificial layer yet. Systems designed not to imitate biology, but to discipline it into predictable industrial output. That tension hasn't resolved yet, and the next 5-year plan will quietly tell us whether it can.